Hello, my name is Mykola Kravchenko, and I am a junior in the Electrical Engineering Department at the University of Michigan. This summer, I participated in an undergraduate research experience working under Dr. Becky Peterson and Wenbing Hu on design and fabrication of thin-film transistors. Firstly, what are thin-film transistors and why are they useful? Thin-film transistors can be made on glass with very thin and transparent films, making them ideal to use for flat panel displays. A traditional field effect transistor, such as a MOSFET, is built on a doped semiconducting substrate. The body is very thick, making a field effect transistor acceptable for a computer chip, but not for an LCD display. On an LCD display, each transistor controls one pixel. Before the addition of TFTs to flat panel displays, the picture on the screen oftentimes could not keep up with fast-moving images. As transistors shrink, their performance improves because less charge is required to turn the transistor on, which means that the smaller we shrink down TFTs, the better our flat panel displays can become. This summer, I improved TFTs by reducing size and developing processes to deposit different metals to use as electrodes. I looked for metals with low sheet resistance that would also have a low contact resistance with our semiconducting channel. The smaller the resistance of the electrodes, the larger the voltage drop across the channel, which makes the transistor be able to turn it on and off at a faster rate. I fabricated transistors in the Lurie Nanofabrication facility using photolithography. Photolithography is a process in which the transistor layers can be defined with selective exposure using UV light. We start with a semiconducting layer that may or may not be already patterned. A light-sensitive chemical called resist is on top and selectively exposed to UV light through a glass mask, which allows the light through in some places and blocks it out in others. The photoresist becomes sensitive to development after exposure, and gets removed only where it is exposed using a solvent. After the patterns are developed onto the photoresist, the metal is deposited on top, by either thermal evaporation or sputtering. Then the remaining photoresist is removed, along with the metal that was deposited on top of the photoresist, leaving metal in the same patterns as defined on the mask. I designed the patterns on the mask to accurately define where the metal and semiconductor layers would be deposited. I also experimented with various processes to increase the accuracy of our patterns. Due to the microscopic size of our critical features, which were only 3 microns wide, the patterning needed to be very exact. I worked with different chemicals and played around with different processes to increase the accuracy of our patterns, all to ensure that our smallest size features would be resolved. Further scaling down of transistors can be done with electron beam lithography. It is similar to regular lithography, only instead of a UV lamp, which needs to be shown through a mask, a small but intense controllable beam of electrons is used to define the pattern. By investigating ways to make smaller and cheaper thin-film transistors, my summer research has helped the advancement of display technology.